We have one last topic for today. Why don't you pause the video and go ahead and write this down. Come back here and let's talk about what it means once you've done that. Okay, so the rational root theorem is a way to factor when we come across a polynomial that we don't have the skills to otherwise factor. So it's used when a polynomial is not easily factored. Here's what the rational root theorem says. It says if p of x, so this is our polynomial in terms of x, is a polynomial with integer coefficients, then every rational solution will be in the form of p over q, where p is one of the factors of the constant and q is a factor of the lead coefficient. Let's go ahead and use that, and I will show you now how to find possible solutions whenever we aren't able to factor in a different way. Let's take a look at problem number 5. Notice that it has 4 terms, so what we would do here is that we would try to factor with grouping. So I would group my first 2 terms together and my second 2 terms together, and then look for a GCF between the 2 terms. So I see an x squared, and I would have a 2x and a minus 9 left. And for the second one, I see a 10, and I would have a 2x plus 3 left. Now, notice what just happened. Normally, if I'm going to be able to factor by grouping, these 2 sets of parentheses would be the same, but these are not the same. So we have what I would call a grouping fail. We failed to be able to factor by grouping. And so the way that we can still try to factor is we know that all of the factors have to, at least, at a minimum, all of the real factors have to be p over q as the format, a factor of the constant and a factor of the lead coefficient. So let's think about our constant. Our constant in this case is 30. So my p is equal to 30. And now I want to think of all of the factors of 30. So I have 1 and 30, 2 and 15, 3 and 10, and 5 and 6. My q is my lead coefficient. Well, my lead coefficient is 2, so my q value is equal to 2, and the factors of 2 are 1 and 2. So I know that all of my factors have to take the form of p over q. Everything that I write here isn't going to be a factor, but it's a possible factor. It's something that we could investigate further to see if it's a factor. That way we're not starting from just an infinite number of possibilities. So I'm going to take every one of my p values and place it over my first q value of 1. So basically, if you put something over 1, you just have that thing, so that's what I'm going to write. I'm going to write a 1, but I'm going to say it could be a positive or a negative 1, because remember, I could have 2 positives that multiply to be a 1 or 2 negatives that multiply to be a 1. Next is 2, so plus and minus 2, plus and minus 3, plus and minus 5, and I've taken care of all the factors down this side. But now I need to go up this side as well, so I'm going to continue with plus and minus 6, plus and minus 10, plus and minus 15, plus and minus 30. And that takes care of all of the p values divided by my q value of 1. But now I have an entire another set of p values divided by the q value of 2. So let's do that. So I'm going to say plus and minus 1/2, plus and minus 2 over 2, plus and minus 3 over 2, 5 over 2, 6 over 2 plus and minus 10 over 2 plus and minus 15 over 2. Yes, this is getting tedious. And plus or minus 30 over 2. Now this looks like a lot, and it is. However, this narrows it down from just every single number you could possibly think of, every real number. So let's go ahead and narrow it down a little bit further, because I notice that some of these factors are kind of the same thing twice. For example, I have 2 over 2, and if I simplify that, well, that's simply a 1, and I already have 1 accounted for. So I can cross that out because we're kind of taking it into account 2 different times. I can do the same thing with 6 over 2 because that's 3. 10 over 2 is 5, and 30 over 2 is 15. All of those are already listed as some of my integers that I have here. All right, so these are the possible solutions. In order to figure out if they are solutions, we would need to test these, and we will do something like that on our next example.